Hi everyone. So let's now see AIMT 3 solutions. Okay, for GATE CSE. So let's just discuss questions of my subject. So let's see this question. This question is from operating systems, and this question was related to synchronization, or you can say deadlock or starvation. Okay, a critical section. So let's see what this question is saying. So they have given that this is some code, right? So this is some code that they have given. And then they're asking that if let's suppose this is the solution of the synchronization problem, then what is the problem with the solution? So which means that they are saying that here there is some special instruction which is atomic instruction, fetch and increment. Okay, this is some you can say a special or atomic instruction. Okay, fetch and increment. And here they are saying that this particular instruction does one thing. It basically returns the previous value. So returns the current value or the previous value, and then increment by 1, which means suppose that inside is initially 0. Okay, then it will return 0, and then increment this value by 1, which means let's suppose this is inside. Then initially if it is 0, then this instruction will return 0, which means a will be 0, and then it will increment the value of inside. Now it will be 1. Okay, like that. So inside is a shared variable, and it will be obviously initialized once. So so let's just see that what are the problems with the solution. Okay, so see here what will happen if you have this was MSQ question. So here inside is initially 0. Okay, inside is initially 0, and then you will execute this fetch and increment, and then inside will become 1, right? But a will be 0 only, right? A will be 0 only. Let's suppose some processor, okay, some process P1 is executing this. So for P1 a will be 0, so a is 0 only. And since a is 0, so this will be false. I mean, this is true whenever a is not 0, right? So this is false if a is 0, right? Since this is false, it will P1 will enter into the critical section. So P1 is here, right? So P1 is able to enter. Now they're asking that whether mutual exclusion is satisfied or not. So is it possible that at this time P2 can enter? So let's just see, right? Let's just see. If P2 now try to enter, since this inside is 1, right? So A value will be 1, and then inside will be 2. Okay, A value will be basically 1, because it will be returning the previous value. So A value will be 1. So it will not be able to enter into the critical section. It will just loop around this loop, right? It will just loop around this loop. So only for one of the process, the a value will be 0, which means this is false for one of the process only. So that is why only one process can enter into the critical section, right? So mutual exclusion, you can say, is satisfied. Why? Because to check mutual exclusion, we want to check if two processes or more than two processes can enter into the critical section at the same time or not. So since two processes cannot enter into the critical section at the same time, that is why we can say that mutual exclusion is satisfied. Understood? Okay. Now let's just see the next thing, which is basically deadlock and starvation. So suppose P1 is here, right? Now can P1 go out? See, P2 is still in the loop. Okay, P2 is still in this do while loop, right? So P2 is still here, right? So P2 is stuck here. Now tell me, can P1 go out? Which means now inside will be 0, and can P1 come again? If it is going out, see, a is a local variable, right? A is a local variable. So if P1 is going out, okay, and if it is coming again, then it can definitely come again. Why? Because a will be 0, and this will be again false for P1, which means P2 might be waiting, and P1 can go out and come again immediately, right? So it is definitely possible. The time that P2 turns come, at that time it will be in the loop only. Why? Because at the time that P2 is coming on its turn, at that time P1 is in the loop. Sorry, P1 is in the critical section. So that is why you can say that bounded waiting is not satisfied, which means starvation is there. Okay, starvation is there. But what about deadlock? Deadlock means that no process is able to execute anything. Is this possible that no process is able to execute anything? So deadlock means, yeah, just a second. Yeah, deadlock means that no process is able to execute anything, right? execute anything. Is this possible? No. At least one process is basically making a progress. So that is why deadlock is not there. Okay. So you can say deadlock is not there. Deadlock is not there because one process is at least making a progress. So deadlock is not there, but starvation is there. Okay. So you can say that mutual exclusion is satisfied. So yes, this is okay, and the above solution is deadlock free. So A and C are the correct answers. Okay. A and C are the correct answers. It was easy question. I hope you understood this question. Now let's just move to the next question. So this question was related to this question was related to banker's algorithm. So which means that they're asking that which of the following is a valid safe sequence. Okay. And if there is no safe sequence, then you can just say that no safe sequence exists. Right. So first to find out the safe sequence basically, which means safe sequence means that which of the following is basically we can execute safely, even if P1 is asking for their maximum need and then P4 is asking for the maximum future need and so on. So for that we first have to calculate the maximum future need. Basically we have to calculate future needs, right? To calculate safe sequence, we should be knowing what is the future need. Okay. So what is the future need? Can you tell me? So this is the maximum. This is currently allocated. So what you can do, you can just subtract, and then you will be getting the future need. Okay. So these are the future need, and the initially initially you can say 2100. This is available. Okay. And these are the future need. So based on this available, can you satisfy anyone's future need? I think P1 is already satisfied. So you can satisfy P1 definitely. So once P1 gets satisfied, P1 will be releasing its own currently allocated resources, right? So currently it is having 0012, so it will release that. So if you add 0012 here, then you will be getting 2121, right? 2121. So 2121 you will be getting. So this is now, you can say this is your current available. Okay. This is now available with you. Now with this available, okay, with this available, can you satisfy anyone's future need? 2112. 2112. I think, yeah, 2112. So I think you can satisfy P4's future need, right? So P4 future need you can satisfy, and then which means you will be adding it's currently allocated. So what are the currently P4 allocated? 2354, right? 2354. So you will add 2354. 2354, which means this is 6, this is 6, this is 4, this is 4. So 4466. So with this 4466, see, P1 and P4 are done. So P1, P4 are done. So with this 4466, 4466, yes. So basically you can satisfy P5, right? You can satisfy P5. So P5 now you can satisfy, and P5 will also release 0332, 0332, which means this will be 8974, 4798. With this 4798 available, can you satisfy anyone's future need? So P1 is done, P4 is done, P5 is done. Among this P2 and P3, can you satisfy 4798, 4798? Yes, we can satisfy P2, right? So P2 we can satisfy. So if you satisfy P2's future need, then people will P2 will be releasing 2000, right? 2000. So which is 8976. So now this is the current available with you, and with this, once P2 is done, can you satisfy P3? Yes, I think you can satisfy P3 also. So basically there is a safe sequence which exists, and I think this is the only safe sequence which exists here, which is P1, P1, P4, P5, and P2, and then P3, right? 14523. 14523. I think B is the correct answer here. Okay. B is the correct answer. So it was easy question. I hope you understood. Now let's move to the next question. So here in this question, they are saying that there is a network, and here you are having flooding. Flooding means like you are basically broadcasting everything. Okay. The packet that someone is sending to you, you're broadcasting that packet. Now they are saying that the source node sends one broadcast packet to each of these three neighbors, right? So which means, and they are saying that everyone is connected to three neighbors. So these are sources connected to three. Now this is also connected to three, but already one is connected. So basically it is connected to two more. Okay, it's not like three more. Okay, here it will be wrong. So two more, two more. Like that there will be a tree. So if you notice, then there will be a tree like this. Okay, I mean network will look like this. Understood? So this is important because some of the students have done it wrong, just thinking that okay, it will be a ternary tree. Ternary tree means that everyone will be having three child. No, it's not a ternary tree, because in the question it is given that every node is connected to exactly three other nodes, right? So which means every node is connected to three other nodes, which means one, two, three nodes, right? So that's why it's not ternary tree. At here it is the three children, but after that it will be just two children. Okay. Now they are saying that uh, at timestamp 10, okay, at T10, at timestamp 10, how many packets you are sending? So basically, at timestamp 1, okay, source is sending. So basically, you are saying at 1, at T1, you are sending three packets. Okay. So at T1, you are sending three packets. Then this is basically, you can say it is at timestamp 1, and then it is timestamp 2. At timestamp 2, how many packets you are sending? At timestamp 2, you will say that you are sending using these three, right? Using these three, which means uh, it will send to 2, it will send to 2, it will send to 2. So whatever was the earlier number into 2, right? I mean, whatever was the earlier number. So T2, you can say T2 will be whatever was the earlier number, 3 into 2. I mean, everyone will be just sending to 2 more, right? Similarly, now everyone again will be sending to 2 more. So basically, you can say at T3 also, 3 into 2, whatever is the earlier number, into 2 more, which is same as saying 3 into 2 square. Okay. So basically, you can say at TT, which means at timestamp any arbitrary timestamp T, you will be sending to 3 into 2 power t minus 1, right? So it is 3 into 2 power 2 if it is t3. If it is t3, okay, then it is 2 power 2. If it is t2, then it is 2 power 1, like that, right? So if it is tt, then it will be 3 into 2 power t minus 1. So they are asking for 10. So it means 3 into 2 power 10 minus 1, which means 3 into 2 power 9. So if you solve this, it will be 1536. Okay, it will be 1536. So it was also easy question. I hope you understood this question. If there is any doubt, you can just let me know. Okay. So 1536 is the correct answer here. Understood? Okay. Now let's just move to this question. In this question, they are saying that you are having two cases. One is that you are having end-to-end flow control, and another is that you are having link by link flow control. So let me just tell you what does this mean. So basically the scenario is like this: you are having three nodes A, B, and C, so which are like this. Okay. Now there are two cases. One is that in one of the case you are having end-to-end flow control, which means the acknowledgement is basically sent by C only, right? So B will just transfer it as it is. Okay. So B will just transfer it as it is. So acknowledgement will be sent by C. So this is the time to transfer for A to B, and then for B to C, D2. Okay. D1 and D2 are the times which are given to us, right? And then basically if it is end to end flow control, it is easy, like it will be d1 plus d2 and d1 plus d2, so 2 into d1 plus d2. But if it is link by link flow control, in that case B is also sending the acknowledgement, and everything is given in the question, right? So the question is saying that in this link by link flow control, or hop by hop flow control, when B receives the packet from A, B immediately send ACK to A while simultaneously forwarding the packet to C. When C receives the packet, it sends an ACK to B, right? So basically, whenever C is receiving the packet, it is sending ACK to B, and B is sending the ACK to A. The entire cycle is complete only when A receives B ACK and B has received C ACK for the same packet, right? So which means that A should be receiving B ACK and B should be receiving C ACK. Then only we will say the entire cycle is complete. So here A is sending packet to C, but in between B is coming, so B is sending ACK, and then C is also sending ACK here. Okay. So what is the total time? The total time we need to calculate is basically D1. First you are taking D1, and then you are taking d2. So it is given that d2 is greater than d1, which means this is simultaneously you are doing. So actually this time will not be considered, this time is not important, because d2 is greater than d1. So basically you can say that d1 plus d2 plus one more d2, right? Plus one more d2. So d1 plus 2 d2. Okay, so this is d2 plus one more d2, where this is the time, right? So d1 plus 2 d2, right? I hope you understood. Okay. So it was easy question. I think for this question, A is the correct answer, right? Now let's see this question. In this question, they are saying that you have TCP, where you are having maximum segment size of 100 bytes and window is 400 bytes, which means window is basically having four packets, right? Four packets. And then they are saying that we denote each packet p sequence number and at uh, p sequence number. So basically each packet is basically p sequence number, right? And the time it is sent is t sequence number. For example, we are sending the packet with sequence number 1000 is p 1000 and we are sending it at t 1000. Okay, now they're saying assume that only p 400 is lost, 1400 is lost. So which means that, see, p 1400 means what will be the sequence numbers? It will be having 1400 to 1499, because MSS is 100 bytes and sequence number is always the first one, right? So if it is P 1400 means like it will start from 1400 and then 1499. So basically this packet they are saying it is P 1400 and this packet has been lost. So this packet will be P 1500, right? Because the starting will be starting byte will be 1500 to 1599. So this packet will be P 1500. What will this packet? This packet will be P 1600, and then this packet will be P 1700, which means P 1600 will be 1600 to 1699. P 1700 is to 1700 to 1799, right? So basically as you notice here that we are having the packets, four packets. I mean there could be any arbitrary number of packets that it has sent before, but this packet has lost. If this packet is lost, then automatically you can say that all of these, I mean still waiting, I mean the window has not forwarded yet, right? So window is still here and you are not sliding the window yet, because this packet has been lost, but no other packet has been lost. So basically these are acknowledged. So that's why you will retransmit it, and you will retransmit it. And then the moment receiver, okay, so the moment you retransmit it, the receiver will say that okay, I have received till what byte? Till the byte number 1700. See, the moment you retransmit it, right? So receiver will say that I have received till byte number 1700, right? So receiver will say that I have received. The moment receiver get this also, it will say I have received 1799. I have received till byte number 1799, right? Receiver will say this. So which means they are asking that what is the highest acknowledged byte? Okay. So what is the highest byte number, or what is the highest act byte? Okay. Once this is retransmitted, or in other words, what is the highest byte number that receiver has confirmed as successfully received? So what is the highest byte number the receiver has confirmed after the retransmission? It will say 1799. This is the highest byte number the receiver is saying that I have successfully received it. So basically 1799 is the correct answer here. Okay. 1799. So, right. So this was also easy question, not that tough question. I hope you understood this question. Okay. Now let's just see this question. This was related to C programming, and this question was easy only, but it was nice question. So one of the doubt that is coming, that since we do not know that what was the initial sequence number in this question, okay, then how to solve this question? See, the initial sequence number is not needed, right? I mean, why we need initial sequence number to solve this question? We, as long as we know that this was lost, it means that earlier packet must have been in waiting. I mean, they are acknowledged, but you cannot basically slide the window, right? You cannot slide the window. But the moment you retransmit it, and then the receiver will say that I have received till 1799, right? I mean, the initial sequence number is not needed to solve this question. Okay. Now let's solve this question. So here in this question they are saying that PTR, basically I have the representation. So let me just copy this. So in this question they are saying that PTR is basically pointing to address of ARR1. ARR1 is this, right? A PTR is pointing to this. But now they are saying that we are making this as integer pointer. Okay, we are making this as integer pointer. The moment you make this as integer pointer, then what will happen? If you do PTR plus 1, it will jump 4 bytes. I mean, PTR plus 0 is this, right? I mean, initially, if it is character pointer, then PTR plus 0 is this, PTR plus 1 is this, PTR plus 2 is this, PTR plus 3 is this, PTR plus 4 is this, right? But here, if it is integer pointer, it will be directly like PTR plus 4, which means it will jump 4 bytes, right? So which means it will directly jump to n. Okay, it will directly jump to n. So PTR is this, but PTR plus 1. So these are the 4 bytes. It will jump 4 bytes. So PTR plus 1 will be pointing here if it is integer pointer. Okay. If PTR is integer pointer, if we are typecasting it. So if we are typecasting it, then it will be integer pointer. And the moment we are printing, right? So PTR plus plus means PTR plus 1. So it will jump 4 bytes. And the moment we are printing it, we are again typecasting it to the character pointer, so that we are just taking the 1 byte from here. Okay. So it will be just printing n. Suppose I have a program like this, that int star PTR, it is basically, you can say, ARR of 1, address of ARR of 1, and then I want to convert this to, obviously it will throw the warning because ARR1 is character. So that's why I can just tell them that okay, let's just treat it like integer pointer. Okay, integer address. And then the moment I do PTR plus plus, it will be basically jumping to n. Okay, till now the things are fine, right? I mean, till now the things were earlier as it was. Okay, so this is basically now PTR. PTR is pointing here. Now suppose in the printf, okay, in the printf, I directly print, okay, this PTR. I mean, I directly do star PTR instead of doing the typecasting again. Then what will happen? Can anyone tell me? Will it print n? Will it print star PTR? Will it print n? No. So basically, it will do one thing. It will just take 4 bytes. Okay, it will take 4 bytes from here. Okay, whatever is the 4 bytes. So it was machine organization, right? So OR. So it will not print these characters. It will print whatever is the I mean, these are the these will be represented by some binary, I mean some ASCII value. So whatever is the decimal equivalent of this NEOR, okay? So decimal value of NEOR, right? It will print star PTR will print the decimal value of NEOR, which means it will be n will be some binary number, e will be some binary, o will be some binary, r will be some binary. So it will be printing the decimal value of NEOR if we are directly printing it. But if you are printing using the typecasting, which means before printing, if you are already doing the character typecast and then you're putting the star, in that case it will just take 1 byte. Okay, so it will be again a character pointer. It is just again a character pointer. So in that case, it will again take 1 byte. So 1 byte means that n will be printed. Okay, so D is the correct answer here. Now, let's solve this. So in this question, they are just asking to print this x, this symbol and y. Okay, sometimes we do not know this symbol. Like this symbol is easy in C programming. This symbol is x or a jor symbol, which means exclusive or. So you can just write 5 in binary using the 32 bits. So it is basically all zeros, and then ultimately it is 101, right? And similarly, you can write 9 in binary. It will be all zeros, and then 1001, right? This is 9 in binary, this is 5, this is 9. And then you can take exclusive or, which means XOR operation. So if you take JOR, then this will be 0, this will be 0, this is 1, this is 1, right? So, and then obviously these are zeros only. So all are zeros only. So it will be 0 0 0 like this, right? So this is basically 8 plus 2, 12. So 12 is the final answer. Understood? It was easy question. How many of you were able to solve this question in exam? I think it was easy question only. Okay. So 12 is the final answer. So that's why 12 is the answer. Now, now let's move to this question. This question was related to recursion. So here we are saying that f of 2026 comma 0, right? So which means here if you notice that a is basically just passed, right? And then this 0 is getting incremented, keep on getting incremented, right? So if we are calling f of 2026 comma 0, then it will be basically calling 2026 into f of, it will be returning 2026 into 2026 comma 1, right? And then similarly it will be keep on doing, right? It will be keep on doing. So it will be again returning 2026 comma multiplied by f of 2026 comma 2, like that, right? Now you notice one thing, that it will stop whenever b is a, which means these two value get equal. So, how many 2026 will come? See, this is how many times lesser? This is basically 2025 times lesser, or here, if you see, this is 2026 times lesser, right? So, if you see here, it will be basically producing 2025 more these values, right? Or in other words, here, if you see, then it will be 2026 into 2026, 2026 times, right? So, 2026 into 2026, it is 2026 times, which is 2026 power 2026. So that's why D is the correct answer. Okay, great. Now let's see this question. This was a bit interesting question, and it was basically focusing on just one thing, that if the importance of this hash define or not. So this hash define is basically just for the macro purpose, which means it does not create its own memory. Okay, so they are saying that which of the following represents the correct representation of this particular this particular fragment, code fragment. So obviously x is 5, so you will be having x5, right? Y will be another memory, and y is pointing to x, right, which is fine. And then zx, right? So this zx will be basically doing one thing. I mean, z will automatically, wherever z is written, it will automatically be replaced by x. So basically you can say wherever z is written, it will automatically be replaced by x. Okay, or in other words, you can say z and x will share the same memory. This is important. Z and x will share the same memory. And then w is another memory. W is another memory, which will be basically pointing to z or x, right? So like this. So which is the correct option? I think C is the correct option, right? So it was easy question, but still it was a nice question, because it was focusing on the thing that you have hash define here. Okay, and hash define does not create its own memory. It will basically ask to share the memory. So that's why C is the correct answer, right? Okay, x and z will share the memory. X and z will share the memory. Okay. So they are asking in this question in order traversal. I think that's easy question. For the in order, you can directly take the projection. Okay, you can take the projection. So which means if you take the projection, this D will be here, E will be here, F is here, G, then H, then K. So D, E, F, G, H, K, something like this, right? D, E, F, G, H, K. So I think B is the correct answer. And then R, S, V, Y. R, S, V, Y, right? Okay. So B is the correct answer here. You can directly take the projection like this. Okay. So it is very nice method for the in order. In order you can just find out in order by the projection. Now let's see this question. So in this question they're asking that if you are searching for, let's suppose, 50, okay, in this while searching for the 50, and the only numbers which are possible are 1 to 100 in binary search tree, then which of the following sequence of keys could not be examined? Okay, they're asking could not be examined. See, if you are searching for 50, then here is actually one important trick that I will just tell you. But before that, tell me, if you are searching for 50, let's suppose, I mean, this is some tree, and let's suppose somewhere, you are going, you are searching, and somewhere, let's suppose 40 is coming, right? 40 is coming. Then will you go to the right of the tree or will you go to the left of the tree? If you are searching for 50, if you are searching for 50, then once you examine 40, you will be going to the right of the tree, right? So you will be going to the right of the tree. That's fine to everyone. Now, in the right, can you ever find 30? Can you ever find 30? Not possible, right? This is not possible. Okay. So I will just summarize what I mean to say, but before that, tell me one more case. Uh, Suppose you are getting some value. Let's suppose 70. Okay. And if you are, or maybe let's suppose 80, or maybe 70. Then if you are searching for 50, then will you go to the right of this or left of this? Like right of 70 or left of 70? If you are searching for 50, then you will be going to the left of 70, right? So you will go to the left of 70. Now, can you ever encounter 80 here? Can you ever encounter 80 on the left? 80 is not possible on the left, right? 80 is not possible on the left. Is this fine? What is the reason? Because we are searching for 50, right? Because we are searching for 50. If we are searching for 50, then the moment we encounter 70, after that, I will go to the left, and after that, 80 is not possible. Okay. So basically, you can say after 40, if you are searching for 50, remember, okay, then after 40, 30 is not possible. After 70, 80 is not possible, right? So, so can you see here that after 40 is 30 possible? Tell me. After 40 is 30 possible? The answer is no, right? So after 40, 30 is not possible. Is this understood to everyone? See, the thing here, there is one trick. The trick is that what you can do, you can see D is not possible and D is the answer. But there is one trick that I would like to convey. The trick is that you can just divide the sequence into two parts. One is that whatever is the element, so you are searching for 50, right? So 50 is at the end, but whatever are the elements which are lesser than 50. So 10, 30 are lesser than 50. What are the elements greater than 50? 70, 60 are greater than 50. So lesser than 50 should be in the increasing order and greater than 50 should be in the decreasing order. Are they in the increasing order? Yes. Are they in the decreasing order? Yes. So A is definitely possible. Okay. Is this understood to you or not? So I think this is clear to everyone that if you just divide the sequence into two parts, right? You just divide the sequence into two parts, and then if it is lesser than 50, should be increasing order. Why that should be in the increasing order? Because once you have seen 10, you will go to the right of it, and on the right you cannot see lesser than 10. Okay, because you are searching for 50, you will go to the right of it, so you will be always seeing greater than 10, right? So here all the values must be greater than 10. Okay, so once you have encountered 70, you will be going to the left, and all the values here should be lesser than 10, lesser than 70. All the values here should be lesser than 80, like that, right? All the values, once you have seen 100, you will go to the left, and all the values here should be lesser than 100. Understood? Okay. So that's how you can solve this question. You can see here that you just divide the sequence into two parts. Okay, just divide the sequence into two parts. One is 100 and 80, another one is 20 and 30. This should be in the decreasing order and this should be in the increasing order. Yes, that is correct. So B is the correct answer. I mean, B is basically not the correct answer. B is, you can say, is possible sequence. What about C? What about C? 120. I mean, this is decreasing. This is the lesser than 50 sequence, and 170 is the greater than 50 seconds. It should be in the decreasing order and it should be in the increasing order. Yes, that is there. So that's why C is also possible. So A, B, C are the possible. But in the D, if you notice, if you divide this into two parts, one is 10, 40, 30, another one is 70 only. So it should be in the increasing order, right? Sorry, it should be in the decreasing order. Sorry, this should be in the increasing order because it is lesser than 50. It should be in the increasing order, but till here it is fine. You will go to the right. But after 40, is there any chance, since you are going to the right, after 40, is there any chance you can see 30? No, right? So that's why D is basically not possible and D is false, right? So that's why D is the correct answer because they are asking could not be examined. Okay, so that's why D is the correct answer. Now let's see this question. This is the next question. So in this question, they are saying that stack is initially empty, and then you are having push and pop, right? So you are pushing n elements, where push is taking p seconds, and there is no gap between any push. After all the pushes are completed, so basically to push all the elements, it will take np time, and then you are taking some random delay of w, right? Which is uniformly distributed between 0 to t. Once this waiting period ends, all n elements are popped one by one. Each pop operation take p seconds. Again, they are taking p seconds, and there is no gap in between. So it will take total time of this, right? So this is constant. This is constant. I mean, this is the total time, and they are asking expected total time. Okay, expected total time. So it will be, since this is constant, it is np plus expected w plus np. Okay. So since W is uniformly distributed, okay. So for the uniform distribution, you can say that the expectation is basically A plus B by 2, right? Expected the or expectation or the average value is basically in the middle. So it is A plus B by 2, which is 0 plus T by 2, which is T by 2, right? Which is T by 2. So hence you can say that 2NP plus T by 2. Okay. So it was easy question, but it was involving probability. So I hope you liked this question, and I hope you were able to solve this question. But that's fine if you are not able to solve. And but I like now you learn this concept, right? So they're just asking the expected total value. You can first find the total value and then take the expectation. Yeah. Now let's just see this question. This was the, I think, one of the most popular question of this AIMT. So here the trick is that we are just asking for to solve this recurrence, but we are keeping order of n here instead of theta n, or instead of just n, we are keeping order of n here. So which means this value could be anything, could be even lesser than 1, it could be 1 upon n. I mean, it is order of n, right? It could be 1, it could be n, it could be log n or anything. So basically, if you take this as n, if you take this as n, you will be getting Tn equal to 2Tn by 2 plus n. In this case, using the Master's theorem, if you apply the Master's theorem, it will be n log n. Tn will be n log n, right? But if you take, let's suppose, as 1, I mean, it could be anything. So you can even take 1. So in that case, it will be n is power log ab. So n and it is 1. So it will be n only. In this case, it will be n only. So sometimes it is n log n and sometimes it is even n. Okay. So so can you represent this Tn as theta? See, theta is not possible because in some cases it is something, in some cases it is something else. So theta is definitely not possible, right? So all of these answers are actually wrong. Theta is not even possible here. Yes, I can say it is definitely lesser than n log n. So if it is lesser than n log n, then it is lesser than n cube also. So that's why D is the correct answer. Okay. See, if here instead of theta, if I have big O of n log n, will it be the correct answer? if I have big O of n log n? Just think about it. So in this case, the big O will be the correct answer. Why? Because big O means it is lesser than equal to n log n, and which is true, right? Which is true. So it is definitely lesser than equal to n log n. Okay, great. Now, so actually, many of the students has marked only this. Okay, they just in hurry they mark n log n, but it is theta of n log n, and theta is even not possible here. So any of this is not correct. Okay. Now let's see this question. This question was related to Bellman-Ford and Dijkstra. So they are asking, will the Dijkstra work here? Will Bellman-Ford work here? Like that they are asking, right? Okay. So you see one thing, that there is no negative cycle. If there is no negative cycle, then Bellman-Ford will definitely work. Okay. So Bellman-Ford will work. Understood? But what about Dijkstra? Let's just see. See, Dijkstra may or may not work. That you might be knowing, right? So Dijkstra may or may not work in case of negative edges, right? I mean, it is not necessary that you need negative cycle. For example, let's suppose, see here I do not even have the cycle, I just have the edges, right? There is no cycle here. Let's suppose this is 1, this is minus 5, this is 5, or maybe let's suppose this is minus 50, this is 10. Okay, so Dijkstra will find out which path has the minimum path from A to C. It will finalize this path, right? It will say that this is the minimum. Okay, but in reality this is the minimum from A to C, for A to C, right? So Dijkstra might not even work for the negative edges, and that is the question asking. In this question also they're asking the same thing: is the Dijkstra working for this graph or not, right? This is what they're asking. So what do you think? See, let's just apply the Dijkstra and then we will see the answer. See here that Dijkstra will say that initially it is 0, these are infinities, right? So this will be basically 1 only, and this is infinity. So this is fine. This will be 1, and then Dijkstra will finalize this, right? And this will be 6, right? And Dijkstra will say that okay, this is minimum, and then Dijkstra will relax this also, and it will say this is 3 and this is minimum, right? Because from 1 here it will be 5, so this is not minimum, so it will say this is minimum, and Dijkstra will finalize that this path is minimum. But in reality, actually, the minimum path is this, right? I mean, the 3 is not the shortest distance. The 1 is the shortest distance. So Dijkstra will not be able to find. Bellman Ford will be able to find. So that's why B and C are the correct answers. Okay, B and C are the correct answers. Is this fine to everyone? Okay. Now let's see this question. This question was linear algebra question, and in this question they're asking what is the value of A for that this particular system will have the infinite solutions. So what you can do, you can simply write this in this form and then use the row reduction, and finally you will be having something like this. Okay, finally you will be having something like this, right? Now to have infinitely many solutions, you want this to be zero, right? You want this to be zero. If it is not zero, there will be no solution, because this is zero and non-zero case. If it is not zero, there will be no solution. If you want infinitely many solutions, you have to have this as zero. So which means 15 minus a must be 0, which means a must be 15. Okay. Understood. So that was easy question. You just have to apply this row reduction. I think I've given it in 1 mark, right? Okay. This was a 1 mark question, so I've given it in 1 mark. Now let's see this probability question. This was nice question, especially it was dealing with the normal distribution. Okay, symmetricity of the normal distribution. So here they are saying that it is given that probability of x greater than or equal to 110 is alpha. Okay, this probability is alpha. Now they're asking that what is this probability if it is normal distribution. See, in the normal distribution, a mean is given as 100. Okay, so in the normal distribution, it is basically symmetric about the mean. It is symmetric about the mean means that if it is 100, then uh, and they are saying that greater than 110. Okay, let's suppose this is 110. Greater than 110, the probability is alpha. Okay, then if the distance is 10, then at the 10 distances there will be 90. Okay, then this probability will also be alpha, which means if greater than 110 is alpha, then due to symmetricity you can say the probability of x being less than or equal to 90 is also alpha. Okay, this is due to symmetricity about the mean. Okay, so because normal distribution is symmetric about mean, and mean is given as 100. So if 110 is 10 distance away from mean, then 90 is also 10 distance lesser than mean. So this probability is also alpha, which means which means these two probabilities are given to us. So which means they are saying x greater than or equal to 110 is alpha. It was given to us, and since mean was also given to us, that's why we have referred that x less than or equal to 90 is also alpha. Now they're asking what is the probability that x is in between 90 and 110. What is this probability? They're asking this thing. So you can say it is same as saying that x is greater than or equal to 90 and x is less than or equal to 110. That's what they're asking, right? But we have less than 90 and greater than 110. So that's why you can do one thing. You can write this same as like this. This is same as, you can say this is same as 1 minus 1 minus uh, the same thing but bar of this, which means okay, which means this, which is same as 1 minus probability of x less than or equal to 90 or x greater than or equal to 110, right? Okay, so it will be, so for the random variable, I mean, see, whenever we say for the any random variable, probability of x equal to a or something x less than or equal to a or something, whenever we have or, then it is easy. I mean, basically you can directly sum. Okay, for any random variable you can directly sum. I mean, generally it is something like this. I mean, you have to basically for the or you also have to subtract some intersection part, right? X equal to a and x equal to b, something like this. Okay, but for the random variables you can directly add because these two things are always independent. Okay, for the random variable. So basically here it will be 1 minus alpha plus alpha, which is 1 minus 2 alpha. Okay. So it will be 1 minus 2 alpha. So what is the correct answer? It was a good question. So how we are solving this? It is basically based on the fact that normal distribution is symmetric about the mean. Okay. Now let's move to the next question. So that's how you can solve this question. It was a good question, right? Okay. So this question was saying that you are having prioritized round robin scheduling. Okay, not just a random or not just a vanilla round robin. It is prioritized round robin scheduling. Here you have two schedulers. One of the scheduler gives the higher priority to the larger quanta. One of the scheduler gives the higher priority to the smaller quanta. and and quanta is also changing. So basically they are saying new processes, whenever they come, the initial quanta is having queue, but whenever a process uses its the entire quanta without blocking, its new quanta is set to the twice of the current quanta, which means from queue it will go to 2 queue, and then the quanta means the time for which it is running, right? Then it will go to 4 queue, then 8 queue, and so on, right? And scheduler A is giving the higher priority to the larger quanta. Scheduler B is giving the higher priority to the smaller quanta. So which scheduler will go for the starvation? Can cause the starvation. Okay. Obviously, the scheduler B. Why? Because see, scheduler is basically saying that whoever is running, right? Whoever is running, let me give the higher priority. Basically, whoever is running completely, let me give the higher priority to that. And since quanta is even larger, it will be basically scheduled for the larger time. So it is just trying to finish the processes. What scheduler B is saying that I am giving the priority to the smaller quanta. If you are giving priority to the smaller quanta, then since the quanta has changed, right? I mean from Q to 2Q, then for the older processes. So whenever new process is coming, you will give the priority to that, right? So you keep on running the new processes, and if the new processes keep on coming, you will never able to execute the smaller processes, right? Either new processes or some processes which are not able to run completely. So basically, the processes, let's suppose there is some process, okay, P1. P1 has no blocking. Blocking means like no IO, okay? So no IO. Let's suppose P1 has no IO. Then P1 will run completely for Q, and this quanta is now 2Q. Okay? Its quanta is now 2Q. Now P2 has some IO, has some IO, and it is not able to run completely from for queue. So let's suppose this is queue time period, and it is not able to run for complete time period, and it is like this needs CPU for this much time and IO for other time, right? So that's why its quanta is it is from queue to queue only. Okay, so P2 quanta is not changing. So scheduler B will prioritize this P2. And there could be, there could be many other. So it will prioritize P2, and P2, let's suppose P2 is having a similar behavior, which means P2 quanta is never changing, and P2 is basically ultimately getting executed and finished. Now some other process is coming into the picture like P3 with the initial quanta like Q, and which is same as P2, which means it is also the IO bound process. Okay. So in that case P1 will never get a chance. So P1 will starve. Why? Because maybe the new processes which are IO bound, which are not completely running on the CPU, they keep on coming, and since they're IO bound, they keep on coming. So that is why you can say that in that case, like P1 will never get a chance, right? If you are using a scheduler B, so scheduler B can cause the starvation. New or IO1 processes always start with the contact queue, so they have the higher priority. A CPU1 process with the contact 2 queue can keep on getting pushed back and again if the processes keep on arriving. Okay. See, it is not like that in the system there has to be infinitely many processes. Let's suppose in this question they add one thing. They add one more line. Okay. Suppose in this question they add one more line. They say that assume in the system there cannot be more than four processes at a time. More than more than four processes at a time. Okay. Still B will cause starvation. Okay. Even if they say that okay, there cannot be more than four processes. Why that is the case? Because for B I'm not saying that that processes should be keep on coming. It is possible that processes which are coming are IO bound. In that case, the quanta will remain to be q only, and with the q quanta they will get prioritized, and then ultimately they will be finished, right? And then p3 is coming, and then p3 is similarly, I mean the behavior is similar to the p2, and its quanta is always remaining q only, and it will get finished, and then p4 is coming. So basically the processes might be finishing with the same quanta q, and p1 is never getting a chance, right? Okay. So I think the question could be more interesting if I add this line, right? So we can add this line because this is something nicer. So we will add this line for the future experience. But yeah, for now, like in both the cases, I can say that the scheduler B will cause that starvation, right? Okay. Now let's just see this question. It was really a nice question. So in this question they are saying that you have p and v operations, and p and v operations are basically used to prevent the race condition, right? But in p and v also we have increment and decrement. For example, this is the implementation of, let's suppose, I think this is the implementation of p. Here we have decrement, okay? So how to prevent the race condition here? The question is about this, that how to prevent the race condition in P and B. This was a good question. So let me just tell you. Actually, this the solution of this question we have already done in our lectures. Okay, in our Go classes lectures, I have told this particular problem in a detail. But let me still tell you. So basically, they are saying that P and V is also having. I mean, in V operation you might be having plus plus and so on. But in P and V you are having minus minus and plus plus, right? And operating system is also a piece of code at the end of the day, right? Piece of code only, written by some operating system designer, but it is ultimately at the is piece of code only. So if you are having P and V operations, and if there are multiple threads which are executing P and V, then will not be race condition? Yes, it will be a race condition. So basically, um, this C option is wrong. Okay, in C option they are saying, because many of the students thinks that C is correct, so that's why I'm telling you that C is wrong. C is saying that operating system execute kernel routines in controlled environment where concurrent races do not occur. No, operating system is also a piece of code at the end of the day, right? So it is also a code. It's also a code at end of the day. So here also the race condition will occur. But how to prevent this race condition? Let me just tell you. So what we do, we actually prevent this race condition by using the hardware support. Okay, we have something like test and set, some hardware supported instructions we must be needing here, which means which means we will be writing test and set here. See, if you remember that this was just vanilla test and set. If we are having this, I mean, for the user critical section, let's suppose we are having this test and set. Okay, okay, this is test and set for the user critical section, but this was not a good idea because of the busy waiting, which means one of the process can be in this while loop, let's suppose p2, and p1 is in the critical section, right? So because of this busy waiting, it is not a good idea. Hence hence not a good idea, right? Not a good idea because of the busy waiting. But here I'm saying that if we use the same idea to the operating system code, see, this is basically we are doing for the users critical section, I mean for the programs critical section. This is a users critical section. But if you do the same idea for operating systems critical section, which means this is operating systems code, right? This is OS code, this is operating system critical section. Critical section. then in this case it is a good idea. Why that is the case? Because this code is fixed. Okay, this code is fixed and hardly of 10 lines. Fixed and hardly of 10 lines. See, I'm not saying this. This is exactly written, even 10 lines. I will just show you in Galvin. Okay. So this code is fixed in hardly of 10 lines. So basically, even if it is busy waiting, which means even one of the process is basically waiting here. See, let me just tell you that all the processes will execute something like this. See, the thing will be like this. They will be having all the processes will be having the critical section protected like this, which means P1 will run this code. Similarly, P2 will also run the same code. Okay, P2 will also run the same code. So let me write P1 and P2 here. So P1 will run this code and P2 will also run the same code. Let's suppose P1 is inside the critical section. P1 is inside critical section and P2 is waiting here. P2 is here. Okay. Suppose P2 is here. Then can you tell me how long? Okay, P2 is here. Can you tell me how long P2 will be waiting? See, this is very short code, isn't it? So P1 will come and it will decrement and will go away, right? P1 will come, decrement and go away. P2 will not be waiting more than one quanta. I mean, whenever P1 is scheduled, it will just decrement and go away. Right? Yes, busy waiting is there. I'm not saying busy waiting is not there, but at for very short period of time, isn't it? Because P1 will come and go away immediately. But in case of users critical section, we don't know, right? It might vary from user to user, from program to program. So we don't know. In case of users critical section, okay. So for the user also, let's suppose I use the test and set directly on the users critical section. Okay. Which means something like this. That P1 is inside and P2 is waiting, okay, in the while loop, suppose, which means P2 is here, P2 is waiting here. Can you tell me for how long P2 will be waiting? You never know, right? I mean, P1 might be taking a lot of time because this is some arbitrary code, right? So P1 might be taking a lot of time here. Because is this guaranteed to since it is users critical section, is this guaranteed to have just 10 lines or something like this? No, right? So P1 may take any longer depending on this critical section, right? So that is why this busy waiting could be longer. But in case if I apply this test and set to the critical section of operating system code, in that case this busy waiting is very short. Okay, so we are applying test and set, but not to the users critical section directly. We are applying it to the operating systems critical section. Understood? So in that case the busy waiting is very less. So P and we are implemented using test and set only. So basically we are making them atomic using test and set or some hardware support. Okay. So it's just that we are not directly taking the test and set for the users critical section. We are moving the test and set to the operating systems critical section. In fact, the same thing is given in the Galvin. If you check Galvin at page number 217, you will see the same thing. It is important to admit that we have not completely eliminated busy waiting with the definition of the wait and signal. Wait and signal means P and B operations. Rather, we have moved busy waiting from entry section to the critical sections of the application programs. So, which means that furthermore, we have limited busy waiting, okay, to the critical section of wait and signal. So, in this case, we have limited busy waiting. And these sections are short. If properly coded, this should not be more than 10 instructions. Thus, the critical section is almost never occupied and busy waiting occurs rarely and then for very short time. An efficient differentiation exists with application programs whose critical section may be long. Okay, users application program or users program critical section may be long, minutes or even hours, or may almost always be occupied. In such case, busy waiting is extremely inefficient. Understood? So basically, we are moving the busy waiting from users program to operating systems program. So that's why I can say for this particular question, B is the correct answer because by protecting only a small critical section of P and V using the hardware supported atomic instructions. Okay. So that's why this question was good. If you know implementation of PNV, you could have solved this question, and it was a natural, question in the sense that PNV has, we invented PNV to solve the race condition, but they itself has the race condition. So how to solve that race condition? This is a natural question, and every gate aspirant should know the answer of this question. Okay. Now I hope you understood that using the test and set we solve this question, this situation. Okay. Now let's solve this question. So this question was, very basic question, not related to synchronization and all. They're just asking what are the possible values of x, y, z. So thread A is having x, y, z like this. Thread B is having x, y, z in reverse order or something like this, right? So see, if the final value of 10 has to be there, then it means that this should be executed after this, right? After this. So basically, x equal to 20 should be executed first and then this should be executed. So basically, you can, for to achieve A, you can execute B completely and then A, right? I mean, if you, this, all of this B is getting vanished because all of the values of A are getting, all of the values of A are here, which means 10, 11, 12, okay? Now, similarly, in one of the option, I think 20, 21, and 22. Yeah, for D, you can execute A first and then B, which means you can vanish all of these values, and then B means 20, 21, and 22, right? You can execute A first and then B. Okay. Is this fine to everyone? Now, let's just check B and C. B could be more interesting. For this B, what we are saying, 20, 11, and 12. Is this possible? That X value finally 20 and Y value finally 11 and Z value finally 12. For X value to be 20, this should be executed last, right? So this should be executed last, which means this should be executed first. I can execute this. And Y is 11 and Z is 12. So basically, these should be executed last also, right? So I can execute this and then I can execute these two, right? And then I can execute either this or this, right? So basically, I can execute this and then I can execute these two so that these values get vanished. So you can say I can execute this and then I can execute these two. Okay. So that ultimately these values get vanished and then you finally have 11, 12, and 20, right? 11, 12 for y and z and 20 for x. So this is possible. You can execute this and then you can execute this, right? Okay. Now let's just see the next option, which is option C. Okay. Option C. Option C is saying 10, 21, and 22. So this is 10, this is 21, and this is 22. For 10 to happen, basically you want to vanish this, okay, and 21, 22, which means y value this you want to vanish and these two are you want to vanish. So you want to vanish these, right? You want to vanish this. So this is this possible to execute this first? I mean, if you want to vanish, which means you have to execute this first, right? Which means, I mean, before this you have to execute this. Is this possible? Yeah, you can execute thread B completely. Okay, which is fine. I mean, this value will get vanished. But you also want to vanish this, right? Which is not possible, right? I mean, once you have executed this, then it is not possible to vanish this element all. So that's why this C is not possible. Okay, C is not possible. See, they are saying that you want to keep this x equal to 10. So it means you have to execute this x equal to 10 after this x equal to 20. So you have to execute this B completely. Then the moment you execute this b completely, then you have to execute these three, right? I mean, you cannot vanish this 11 12. So that is why this c is not possible. Okay, so c is not possible. Understood? So this is possible, this is possible. But there are some other possible and non-possible combinations. Let's just see all of them. For example, I have written here, these are some possible and non-possible combinations. So I think for the possible, we have done 20 11 12 also. 20 11 12 this is done. Thread A completely this is done. 20 21 22 this is also done. Let's just check if this is possible. 20, you want x to be 20, by to be 21, and z to be 12. Okay, you want this combination. Is this possible? If you want x to be 20, then then basically you want to vanish this. Okay, so you want to vanish this, you want to execute this, and then by and z, by to be 21, which means you want to vanish this. Okay, and z to be 12, which means you want to vanish the opposite. Okay, which means this, right? Yeah, 20 21 and 22 and 12. So yeah, it is possible you can execute these two, and then you can execute this, right? So you can vanish these three, and then yes, this is possible, right? Okay, so this is possible like that. Let's just see some of the impossible values. For example, is this possible to vanish? Is this possible to get 10, 11, 10, 10, 11, 22? Let's just check. Okay, for 10, 11, 22, what we need to check, that you want to keep this, right? You want to keep this, and you want to keep 22. You want to keep this. Okay. If you want to keep this, you have to execute this completely, right? And then only you can execute this. Basically, you have to execute this jet first. The moment you execute this completely, because you have to execute this, you have to execute this jet first, right? And then you have to run this. So the moment you run this completely, you cannot keep this x and y. So that's why it is impossible. So it is impossible. Okay. What about 10, 21, and 12? So let's just check. 10, 21, and 12. Okay. See here, you want to keep this 10, you want to keep this 21, you want to keep this 12, right? So if you want to keep this, you want to vanish this, which means you have to execute this completely. If you have to execute this completely, then you cannot keep this 21, right? Because this 11 will get overwritten. So that's why this is also impossible. This was impossible. What about 10, 11, 10, 21, and 22? Let's just check that. 10, 21, and 22. So see here, see these two are not possible. See here, you want to keep this 10, 21, and 22. You want to keep these three, right? If you want to keep this, you have to execute this fully, and then only you should be executing this. But then this will get overwritten, so that's why this is not possible. Okay, what about 20, 20, 11, and 22? 20, you want to keep this, 11, you want to keep this, and 22. So let me go to the next page. 20, 11, and 22. Okay, you want to keep these three. What about this? If you want to keep these three, then you have to basically execute this first. Then you can execute this. That's fine. Yeah, this is interesting, right? So see, I mean, X value you can have. Basically, you can execute this, so that everything is fine. And then after that, basically, you want to keep this y equal to 11, right? Now, if you want to keep this y equal to 11, you have to execute this, right? You have to execute this. This y equal to 21, you have to execute first, and then y equal to 11. But the moment you execute this y equal to 21, then you will not be able to retain this z value, because z value will get overwritten with this 12. Okay, so this was interesting, and this is also not possible. So I hope you understood that that why some of the values are possible, why some of the values are not possible. Okay, great. Now let's just move to the next question. So let us now solve this question. So in this question, they are saying that suppose one network is given to you, and here there is one node D which is falsely claiming that it has a link from D to A. Okay, so it is a direct link to A with a cost one, even though such link does not exist. Okay, suppose it is falsely claiming, and all of these links has the cost one. Okay, so all of these links has cost one, and it is falsely claiming that this also has the link of cost one. Okay, routers compute the shortest path using the either distance vector, which means DVR protocol, or the link state protocol. In other words, node D is advertising incorrect routing information to rest of the network. Which one of the following is correct? DVR, which means distance vector, can detect this bogus link, but link state cannot, and vice versa. Okay, so they are just asking that suppose D is falsely claiming, then which of the following is correct? Okay, uh, so see here that in DVR or in distance vector, what happens that you basically get the vectors, or you get the updates from the neighbors, right? So C will be getting the updates from D and B only, right? And similarly, E will be getting the updates from F and D. So basically, you will in DVR, since you're receiving the information from the neighbors, you will never be able to know that whether this information is correct or wrong. But on the other hand, in link state, there is a flooding, right? I mean, in link state, A will get information from everyone. A will get information from B, from C, from D, from E, from F, from G. So since it is getting information from everyone, so it will get to know that okay, there is a link which is D to A or not, because in link state basically we can form the entire network after getting all the vectors, right? So when A is getting the vectors from B, from C, from D, from E, from F, from G, right, from everyone, okay, and similarly everyone else will be getting the vectors from everyone else. So there you will get to know that okay, the information is basically something very different from the information from every other node, right? So in distance vector, you can detect this bogus link, but in link state you cannot, right? So sorry, in distance vector you cannot detect, and in link state you can detect. Okay, so that's why B is the correct answer. So this question I have taken from some university. So here the answer is also directly taken. So basically they are saying with distance vector, each node maintains each distances only to the next hop and the distance to that hop. Since the node doesn't know the path to the destination, in general it cannot discover the discrepancy between info provided by D and A. Okay. For example, node C has no choice but to believe D that it has passed to A. But in linked state, every node eventually nodes the entire topology. This way, the node will see that D claims that it has linked to A, while A doesn't. Okay, this is important. Okay, see, D is claiming that it has node to it has basically linked to A, but since A is not claiming the same thing, right? So it means D is basically they will get to know that there is some problem. Okay, either D is lying or A is lying, so they can detect this bogus link that there is something wrong. But in distance vector, in distance vector we are just receiving the distances from the neighbors, so we will not be able to detect. Okay, now let's see this question. So in this question they are saying that here you are given that IP address is of just 4 bits long, okay, not the 32 bit. So suppose a router that uses the longest prefix matching and has the following forwarding table. Let's suppose that there is a following forwarding table, and IP addresses are just 4 bits long, okay. Now they are saying that it is given the destination address 1001 is forwarded to output interface C. Okay, so they are saying that suppose that 1001, okay, 1001 is forwarded to C. So what are the possible values of X? Let's just find out what are the possible values of X. If 1001, which is the complete IP address, I mean, since the IP address is just of 4 bits, right? If it is forwarded to C, it means X must be basically either 1001. Okay, so what are the possible values of X? X could be either 1001, or what are the other possible values? X could be basically, it has to be, it cannot be just 10 or something. I mean, it has to be greater than 10. It has to be longest match, right? So it has to be the longest prefix match. So X can be either this or greater than 10. Maybe it is 100, right? X can be 100 also. So either it is 100 or 1001. Okay. So what are the two possible values of X? 100 and 1001. So P is the number of possible values of X, which is basically 2. Okay. Q is saying number of distinct 4-bit IP addresses, 4-bit destination addresses that is forwarded to B. So how many IP addresses that you believe forwarding to B? Whichever is getting starting with 1, right? Okay, whichever is getting started with 1. But 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 so basically there are 8 addresses which are starting with 1. Okay. But out of those 8, whatever is starting with 10, okay, whatever is starting with 10 basically will be forwarded to A, right? So basically you can say out of this 8, okay, whatever is starting with 10, which means these 4 addresses which are starting with 10, okay, which will be forwarded to A. So 4 addresses will be forwarded to A, right? And the remaining 4 out of this 8, okay, out of these 8, the remaining 4 will be forwarded to B. Okay, I mean, don't worry about the C and D for this part B, because for this B you don't have to worry about C, because C is actually the longer one, okay, which is 100, right? So basically you can say 4. Okay, so 8 minus 4, which is the 4 addresses which will be forwarded to B. And the possible values of X is 2, so basically P plus Q is 2 plus 4 is 6. Okay, that's fine. So basically, this question was just asking to check if you are aware about this longest prefix match information or not. I mean, this concept or not. And this concept has been asked in GATE earlier also, but not in this format. So we have asked in this format. I hope you understood this question, right? Okay. So see, now you might be a little confused that why this C is not affecting this B the way A is affecting. See, A is already saying that whatever is, we have already considered that whatever is starting with 10, right? That has been forwarded to either A or C. Actually, C is also 10 or 01, 1001 or 100. So it has already considered, like we have already considered, when we are saying that whatever is starting with 10, we have already considered the C. Okay, so you don't have to worry about the C. So basically whatever is starting with 1, but whatever is starting with 10, or whatever is starting with 100, 1001, these will be forwarded to A and C. Otherwise it will be forwarded to B. So basically there are 4 addresses which will be forwarded to B. And what are those 4 addresses? It will be 1 1, and then 0 0, 0 1, 1 0, and 1 1. Okay, so basically these are the four addresses which will be forwarded to B. Okay. Now let's see this question. This was a little interesting question, in the sense that this question is asking that which values are getting swapped. Okay, x, y, u, v, a, b, and so on. So here u and v are pointing to x and y. So basically this is x, this is y. Okay, this is u, this is v. U and v are pointing to x and y. And then there is a and b which are pointing to u and v. Okay, so a and b are the double pointers. So a is basically pointing to u, and u is eventually pointing to x. Okay, so this is the diagram that we have. Now they are saying the swap a comma b. Okay, so in the swap function we are basically swapping whatever a is pointing to, because star temp. Okay, I mean, basically star a and star b we are swapping. Star a and star b means we are swapping this u and b, content of u and b. Okay. So what we are swapping, we are actually swapping u and b. Okay, that's all. I mean, we are not swapping a and b, we are not swapping x and y, we are just swapping u and b. So what is the answer here? Our answer is b. Okay, answer is b. Understood? So that's easy question, answer is b. Now let's see this question. So in this question they are saying, consider the following c function, right? So this is the c function that we have here. They are saying that jip is one function. If a is null, it is returning the whole other linked list, which is b. If b is null, it is returning the whole other linked list, which is a. Okay. Now we are calling with this a and b. I mean jip a and b. Okay. Now what this function will does, it will say that okay, let me just take the a next and b next. Okay, so basically a is like this. Okay, age 5, 7, 17 and null. Okay, a is this, and b is 12, 10, 2, 4, 6 and null. Okay, now a dot next means this. Okay, so basically this is like next a and this is next b, right? Now what we are doing, we are saying a dot next to point 2. So we are saying this a of next, okay, which means this a dot next, right? This should be point to b, which means this 5 should be pointing to 12. Okay, this 5 should be pointing to 12. And then this b node next, which means this 12. Okay, this 12 should be pointing to this b node next should be pointing to next. I mean, basically now here we are forwarding. Okay, this from starting from 7 and starting from 10. Okay, so basically we are saying next and next b means starting from 7 and starting from 10. So what is happening here, that we are saying that 5 is pointing to 12, and what 12 is pointing to, what b dot next will point to, it will point to whatever this zip returns. Okay, whatever this zip returns. So basically zip means 7, 17 null, comma 10, 2, 4, 6 null. So basically let me just tell you here that 5 will start pointing to 12, and then 12 will point to the remaining this, right? So basically it will basically do one thing. Given this 5 will point to 12, and then 12 will point to whatever the next thing. So similarly the 7 will point to 10. Okay, I mean, since this is a recursion, so 5 will point to 12, and then 7 will point to 10, and similarly 17 will point to 2, and then, and since it is null, so it will return the same, which means 4, 6 and null will keep on pointing to each other. So basically it was a was 5, 7, 17 null, and b is 12, 10, 2, 4, 6 null, right? Now now 5 will point to 12, similarly 7 will point to 10. Okay, so it happens like this. 5 is now pointing to 12, and now what 12 is pointing to currently you don't know, right? So basically it's a recursive call, right? It will basically point to whatever the recursion will return. Okay, so 7, I mean whatever the recursion will do, I will just tell you, but inside this 7 will point to 10, and then this 17 will point to 2, and then 4 will point to 6, and then 6 will point to null. Okay, so something like this. Okay. So any recursion, let's just see what the recursion is doing. Recursion is returning A. Okay. A means A means what? The first linked list. Okay. Pointer to the first linked list. Right. So pointer to first linked list means that the pointer to, if we are calling with this zip, okay, the pointer to 7 it will return. Right. So the pointer to 7 we are returning. So which means this recursive call will return pointer to 7. Okay, so every of this is a recursive call. Okay, every of this is a recursive call. So you can say like this. Okay, and then here one more like this, right? So here you can say ultimately we are returning to the first recursive call, which means it will be returning to 7, 10, 17, 2, 4, 6 null. So basically we are pointing to the alternate things. 5 will point to 12, and then so 5 12, and then 7 10, then 17 2, and then there is nothing, so that's why 4 6 null. Okay, so that's how it is being done. So you can say that 5 12 7 10. I think A is the correct answer. Okay, so 5 12 will get called, and then whatever it returns, the 12 will point to that. So it will return the pointer to the first linked list, because it is returning to the A means the pointer to the head of the first linked list, which means it will return the pointer to 7. Okay, so 12 will start pointing to 7, and 7 will point to 10. After this call 7 will point to 10. Okay, 7 will point to 10. So this is how it is happening at the return time. At the return time, basically this will 2 will start pointing to 4. So basically, let me just tell you as a recursion. I think the idea is conveyed, but still let me just quickly tell you as a recursion how it is happening. This is 5 7 17 null, and then this is 12 10 2 4 6 null. Okay, so here we are saying that the as a recursion, what will happen? 5 will first start pointing to 12. Okay, and then there is a recursive call. Here it is a recursive call, and then you are saying that now this 12 is actually waiting. Okay, 12 is waiting, and the recursion will just stabilize this link. Okay, 12 is waiting to point. Okay, so 12 is waiting, and then so see here 5 is pointing to 12, and now 12 is waiting whatever the recursion returns, right? So recursion will return, since you are passing, okay, since you are passing this and this linked list, okay, in a zip. So recursion will return the pointer to the first linked list, which means it will return 7. Okay, and because of the recursion, 7 will point to 10, and then 10 will be waiting whatever the recursion returns. Okay, so recursion will actually return 17. 17 will point to 2, and 12 2 will be waiting whatever recursion returns. So 4 6 null, it's like that, right? So recursion will return, here it will return 7, here it will return pointer to 17, here it will return 4. Okay, so this is the final linked list that we will be getting. So A is the correct answer. Okay. Now let's see this question. This was interesting question, and it was related to DFS parenthesis theorem. Okay. So what does this mean? Let me just tell you. So they are saying that in DFS, okay, you are given DFS traversal and start and finish time assigned to the vertices, right? You are given start and finish time. In a DFS of directed graph, it is possible to have an edge between two vertices u and v, such that u has start and finish times as this, and v has start and finish time as this. So they are saying DFS is directed graph. DFS in directed graph. Okay. So u has the finish time of 10 and 40. So u has the finish time of, I mean, start and finish time of 10 and 40, and v has the start and finish time of 30 and 50. Okay, so u is starting from 10 and 40, and v is starting from 30. Okay, 30 and 50. Is this possible? Do you know DFS parenthesis theorem? So there is a theorem which is called DFS parenthesis theorem. I have taken this lecture on the YouTube. You can check YouTube lecture, okay, for the DFS parenthesis theorem. It says that no to interval can overlap. I mean, can basically interleave like this. I mean, one of the either the intervals could be completely disjoint, or they are overlapping. or they are overlapping like this. Okay, I mean they are completely inside. It cannot be like this, right? Just like the parenthesis, which means if the parenthesis is starting like this and another parenthesis like this, then they are completely disjoint, or the another parenthesis is basically under the outer parenthesis. The inner parenthesis should be under the outer parenthesis. It cannot be the case that one parenthesis is open and then another is open, then this is closed, right? It cannot be the case. Okay, I mean, this is not possible basically. Okay, this is not possible according to the DFS parenthesis theorem. So that's why A is wrong. But let's just see other options also. They are saying in undirected 520 and 3050. Okay, so 520 and 3050. Yes, this is definitely possible. Okay, whether it is undirected, directed doesn't matter. This is possible. So basically, this is not possible in any of the graph. This is possible in both of the graph. Okay, either it is directed and directed doesn't matter. Yes, this is possible in both of the graph. This is not possible in any of the graph. Okay, doesn't matter whether it is directed or not. What about this? What about this? In DFS of directed graph, it is possible to have an edge between two vertices U and V such that U has a start and finish time of 520. So basically, it is actually possible, right? Now let's just see option C. 520 and 3050. Just a second. In undirected graph, it is possible to have edge between. Sorry. Basically, in undirected graph, okay, this is important. In undirected graph, is this possible? This is 520 and this is 3050. Basically, they are saying in an undirected graph, it is possible to have completely disjoint. Which means once this is finished, then you are starting this. Actually, in an undirected graph, since it is undirected, then it is not possible. Why? Because because in undirected graph there is no cross edge. I mean, this is possible only when you have a edge like this, right? I mean, once it is finished, then see something like this. Okay, this is U, this is V. I mean, there is edge like this. You are finishing U. I mean, you have some its own things, and there is V, and V has its own things. You are starting U and you are finishing, and then you are starting V, right? So this is possible. This is possible in directed graph, but in undirected graph it is not possible because cross hatch is not possible in undirected graph. So I'm sorry about it. So basically, this is not possible, right? This is not possible in undirected graph. Okay. But is this possible in directed graph? Yes. The same thing is possible in directed graph because of the cross hatch. Okay. Because of the cross hatch. Cross edge will be from this vertex to this vertex, right? This vertex to this vertex. Now, now they are saying there is one 10, 20 and 15, 18 in directed graph. So U is 10, 20 and V is 15, 18, right? So V is 15, 18. So 10, 20 means like this and 15, 18 will be under this, right? So this is 10, 20, this is 15, 18. Yes, this is definitely possible. But now they are saying, I think, something else. They are saying if this is possible in a directed graph, then VU, okay, must be back edge. Okay, in that case, VU must be back edge, which means this is U and this is V, right? So now they are saying in that case, VU must be back edge. See, if you are starting U, okay, and while exploring U, you found V. Then if there is an edge VU, then it must be back edge. Yes, that's true, right? I mean, that has to be back edge. If after exploring U, you are finding V, and then if there is an edge between V and U, then it must be back edge, right? Because V has been found after U because of this these nestings, right? These nesting intervals. So you can say yes, this is possible. So C and D are true here. Okay. Let's now see this question. I think this question was easy one, but still let's just see this. So in this question they are saying that you have applied insertion sort, right? So you have applied insertion sort, and they are saying that the four iterations are over. For the insertion sort also, four iterations are over. So in one iteration, basically in insertion sort, what happens? In one iteration, you will basically settle. So in one iteration, you will settle this element, right? I mean, this element will get its correct position. Then this element, second iteration, third iteration, fourth iteration, right? In four iterations, these elements will get its correct positions, right? In insertion sort. So basically, you do not know about anything about these elements, and these elements are anyway there, right? I mean, they are not moved. Okay, even though this has not moved, but we have used it. Okay, it doesn't mean we have not used it. So basically we cannot say anything about these elements. So basically in any option, if these elements are being used, which means this option, okay, I think only in this option this element is being used. And so basically, by the way, like these are the Pokemon wedges. Like I think you already know this. Some of the people know this, and some of the people appreciated it. Okay, so thank you. This question I have taken from Berkeley University. So this was a Berkeley University from which I have taken this question. Okay, so yeah, this option for about A we cannot say anything, right? About A we cannot say anything. What about option B? In option B, they are saying basically in the question they are saying you are arranging from least to greatest, which means in increasing order, right? Option B is saying that this wedge is greater than this hurt, right? So if you compare these two, and since it has basically replaced this, right, which means this must be lesser. So till now these are shortest, right? Till now these are shortest, you can say. So if you compare these two, no, this is false, right? I mean, if you compare these two, this is false. If you compare these two, yes, this is greater, so this is true. Okay, because this is the shortest, right? I mean, this is basically already sorted. Okay, this array is sorted. Now, if you compare these two, this is greater, which is wrong. Okay, is the only C correct answer here? Okay, so I think only C seems to be the correct answer. Let me just check. Give me a second. So anyway, like actually this is greater, right? So among these two, since this is coming later, so this is anyway greater. So B is also correct, right? This is very simple observation that this is coming later. So this is anyway greater. So B and C are the correct answers, right? So let me just check for this question. Yes, B and C are the correct answers. Okay. And I think many people have appreciated about the wedges that we are using. That I spent an additional 2 minutes admiring the Pokemon gym wedges. I like the question, though it was very easy. Okay. Yes, it was easy question, but yeah, I hope that you people liked it. Now let's move to this question. This was also very easy question. So here they're asking about this conditional probability. So this conditional probability is basically probability of x equal to 2 comma y equal to 2 divided by probability of y equal to 2, right? So x equal to 2 comma y equal to 2, which means it is a joint probability and it is given here. This table is for the joint probability. Okay, so x equal to 2 y equal to 2, x equal to y equal to 2 is 0.1. So it is 0.1 divided by probability of y equal to 2. Probability of y equal to 2, which means basically probability of y equal to 2 will be, you can say, it will be probability of y equal to 2 when x is 1 plus probability of y equal to 2 when x is 2, right? I mean, you can just sum over this row. Okay, so you can just sum over this row, it will be 0.4. So which means 1 by 4, it is 0.25. Okay, so 0.25 was the correct answer here. So some people were saying that it is not in the gate syllabus. See, if the conditional probability could have been the gate syllabus, then why not the joint probability? I mean, conditional probability cannot be even solved using without the joint probability, right? So joint probability obviously is there in the gate syllabus. Okay, obviously the easy questions one, like not the tough questions. So it was a complete discussion of all the questions. We hope that you like this AIMT. And there has been, I think, like 4,261 students has appeared in this AIMT. which was a huge number. So thank you everyone for participating in this AMT. If you have understood everything, this was a short session, and if you have understood everything, just let us know in the comment section. Okay. So thank you everyone.